I've given you 3 different things, and what you should have out at this point: the paper that describes your final exam option, one of the 2 options. We'll talk about that first. Metals and non-metals is the second thing we're going to cover, and then protons, neutrons, and electrons. That will go on the bottom of your stack. On the very top, though, you should have your homework, a look at the periodic table. We're going to be grading that here in a little bit. Plus, you want to have your periodic table out. Okay? If you're someone that is always a little slow with your note-taking, keeping up with the notes, you might want to have a highlighter out as well. So that's 5 sheets. The 3 I gave you, your homework, the periodic table, your notes, of course, that makes it 6, and a pen or pencil, of course. If you got a highlighter, that would also be useful. Okay, so lots of different things to manage here. First of all, before we get into today's lessons and the terms on the board here, let me talk about the final exam. We've already had our 1 chemistry quiz. We'll have the next one next week. It may not match the calendar, just so you know. And then the final chemistry exam. But what I'm talking about is the final exam, which covers everything for the entire year. You have 2 options, and they're both listed here on my website. If you go to final exam, you'll see a section that's very similar to what I handed out in this paper. So let me explain what this paper is for. If you want to read the requirements, they're also on this section. But there are 2 options. You can either take the comprehensive final. It's a test of over 100 questions covering stuff since the beginning of the year. If you are someone that does poorly on tests, but you really feel you learned a lot this year and maybe didn't show it on tests, you may choose to do the summary paper. Do not, I repeat, and this is being recorded so I can refer your parents to it later and say I told you this. Do not do the summary paper if you cannot follow every single direction listed on this page. Okay? It's very frustrating. I don't like to be the bad person and have to give people zeros because they don't follow directions, but if I can teach you nothing more than the importance of following directions, in my mind I've succeeded. That's more important than all the other science content you've learned, because that's a big key to your success. And like the Rube Goldberg machines that you're turning in for extra credit, of the 4 I've had turned in, guess how many follow the directions? 1. Only 1 person followed the directions. It specifically says in there, it must include 8 different machines. Some of you have 8 machines, but they're not different. You have 2 decline planes, 2 first-class levers, and it really makes me sad to have to give you no credit for all that work you put, but it's not me being mean, guys. I wrote it down in the directions. I reminded you repeatedly, read and follow the directions. And I would hate to see you get a 0 on the final exam, which is very important, when you had all the directions right there. Okay? Kind of like doing that summary paper over there about the Explore Science Center. Make sure you've read and followed all those directions before you turn it into me. Of course, tomorrow's the last day. But I point this out to you now, and I give you this sheet now because the final exam is already on my calendar. It's, I believe, the last Monday or Tuesday of that final week. And what will happen is if you choose to do the summary paper, rather than taking the test that day in class, you will turn in this assignment to me. This assignment is a minimum 5 pages typed in black ink, double-spaced, a normal 12-point font with margins of exactly 1 inch. Okay? It says slightly more is allowed on the bottom, and I'll show you exactly what I mean by slightly more. You should measure the printout to make sure it's 1 inch. A cover page is not included in the 5-page count. And you're not following the 5-paragraph format. You're following what I've asked for in the directions, which say 8 paragraphs, 1 for each unit. So if you look here as your guide, you can see 1, 2, 3, 4, 5, 6, 7, 8. A paragraph talking about each of the units we've covered. What I hope to see is what you actually learn from each of those, okay? I don't want you just copying stuff off of worksheets from that particular unit. I want you to teach me like you would be teaching your little brother or sister. That's how it describes it here. What did you remember? How was that useful? Why was it interesting to you? That'll help me out. It lets me see what you really got out of the experience, rather than just copying over a bunch of facts from the unit that you copied off of a worksheet. Okay? So you're teaching me over. You're telling me again, what do you remember from electricity and magnetism and from making your circuit? What things will you take and go forward with? You know, if you were teaching the same stuff over to a kid, what could you teach them that you learned from those units? All right? So exactly 8 paragraphs, not 8.5, not 9, and 5 pages minimum. The reason you have this thing that has the 2 boxes is because I got in a debate one year with a parent. He claimed his daughter's paper matched the requirements. Well, the requirements say 1-inch margin. 1-inch margin would fall right between those 2 lines, okay? And I said, no, if you measure it with a ruler, it's 1.25 inches. And he says, well, that's close enough. And I was just dumbfounded. He was an engineer, and he's telling me that 1.25 inches is close enough to 1 inch. Can you imagine if you're making parts for a machine? It ain't gonna work if it's off by 1/4 inch. You have to learn at some point in your life that details are important. Accuracy, precision is important. Now his argument is there's no such thing as an exact measurement because there's always human error. Well, fine. Here's my solution to that. Take this paper, you print out your paper, you hold it up, and you put this on top, this template on top, and your paper underneath. You hold it up to light, and you look. When you look through there, you should be able to see the edge of your writing. It should fall between those 2 box lines. Got it? If it doesn't fall between those 2 box lines, you didn't follow directions. So this is your guide to use. Any questions on the summary paper? What I want to do now is we're going to go through and talk about metals and nonmetals, what they have in common, what's different. If you are slow at note-taking, that's where the highlighter comes in. You can highlight as we go through this stuff in the text. Okay? Now you may be saying, well, why would I bother highlighting it here when I have to put it in my notes? Or why would I bother putting my notes when I've already got it here? Well, the answer is when you copy the information over by hand, you learn it much better than just reading it. Okay? So even if you have all the information you need on this sheet, you should still write it in your notes because that's part of the exercise of learning it. So as we encounter each definition, you can add it to your notes and or highlight it on this paper. But you should copy it over to your notes eventually. That way you have it all in one place too. Metals. Metals are usually good conductors of heat and electricity. You knew that. Now, of course, some metals conduct electricity a lot better than others. You two can move up if you like. Get a little closer. Second fact, metals are malleable. They talked about this on the video yesterday. That means that they can be reshaped, like tin foil can be reshaped. An iron bar can be bent and reshaped. Doesn't mean you can do it with your bare hands necessarily, but it can be reshaped. Some substances you go to bend and they just are too brittle and break. Metals can typically be reshaped. The third fact there is that it is ductile. Ductile means it can be pulled or drawn into a wire. You can shape it into a wire. Like an air duct is a long skinny tube kind of thing. Well, that's what we can do with metal. Metals usually, not always, but usually have luster. That means they're shiny. And metals have 1, 2, 3 outermost or valence electrons. This is an important concept here, the valence electrons. Okay? As we look at a model of an atom, we know that we have our protons and our neutrons on the inside. And we know that the electrons, they fill in these spaces around the outside, these orbits. Some of the orbits are close and some are farther out. Okay? But Each of these orbits, or shells they're called, sometimes they're called energy levels, each of these orbits can contain a certain number of electrons, okay? And we get shells that get farther and farther and farther away from the nucleus, the center of the atom. When we refer to the valence shell, that means it's the last shell that has electrons in it. Now there's none out here. There's no electrons orbiting out here. So this would be referred to as the valence shell. And these two electrons would be the valence electrons. And when we're talking about a metal, it usually has 1, 2, or 3 of those electrons in the outermost shell. And you're going to learn as we get into this more today that what is out here in that outermost shell, the valence shell, is real important when it comes to how that atom presents itself to other atoms. Will it react with other atoms? Yes or no? What will it do when you bring it up to a different atom? Okay? And there actually is an ideal number of electrons that all atoms would like to have in their outer shell. Does anyone know that magic number? Well, let's look up here. What would this like to have in this shell? 8. 8 is the magic number. And if we have 8 electrons in our outermost shell, it's a happy, happy atom. It's stable. And if it's stable, do you think it will react with other atoms? No. It's be like, I don't need you. I'm good by myself. I got all the electrons I want. I'm happy. Okay? Any more than a ball laying on the ground is suddenly going to jump up with energy. Okay? It's stable. It doesn't, you have to do something to it. You have to raise it up to make it roll downhill again. Okay? We have to knock some electrons off. This is not stable. This wants to combine with something else. Okay? And if we put it in the right situation, it will. Let me back up here now. So now you know what I mean when I say valence electrons. The valence electrons are the outermost electrons, and they're that the face, if you will, that the atom presents to other atoms. You know, they don't know what's inside, just like people don't know what's inside your heart. If you're a good person, if you're intelligent or witty, they often just judge you by what's on the surface. Well, other atoms judge other atoms based on what's on the surface, the number of electrons that are on the outside. Yes?
Wait, so does the electron cloud, like,
I'm kind of oversimplifying it, but yeah, in a way it does. Because remember, those electrons are moving, what they say, 1 billion times a second or something like that, something outrageous. They're moving very fast, and we can't just see one. Ooh, there's an electron, there's an electron. So when we say electron cloud, we really mean that electron, or those electrons, are likely to be found in this general area. And yeah, they're buzzing around so fast that it's like bees around the beehive. You're not going to see that actual hive until you can get rid of the bees. Okay? So you'd have to shoot inside that atom and knock off a proton in order to get it out of that electron cloud. Okay? Not all atoms have a whole bunch of electrons around the outside. Depends on the complexity of the atom. Okay, the other fact is that metals tend to lose electrons easily. Well, you knew that. That's what makes them a good conductor. And what electrons do you think they're losing easily? Which electrons? The outside, called the valence electrons. You need to get familiar with that term. That's a real important concept in chemistry. Metals form alloys easily. This is the 3rd time now I've thrown the term alloy at you. What is an alloy?
it's a combination of 2 metals
And why do we combine them together?
to make something more versatile.
Yeah, when we're making an alloy intentionally, we're mixing metals together so that we can make something that has the properties of both. Like the gold jewelry is an alloy of gold and silver, or gold and copper, because separately one's not very valuable but is sturdy, the other one's valuable but it bends and is weak. When we combine them together, we get both properties. Okay? Alright, moving on, oops, wrong direction. Moving on to nonmetals. Nonmetals, think of gases and solids that are dull and brittle. these things have a low melting point. When I say low melting point, does that mean it requires a lot of heat or very little heat to melt it? Very little. As opposed to a metal, which usually has a higher melting point. So nitrogen, oxygen, hydrogen, those are all examples of obviously non-metals. And then there are all the dull, brittle solids with low melting points. If you look to the right of the zigzag line that you drew on your table, the one you turned into me, those are all the non-metals. They often combine with metals to make compounds. Remember, a compound is a substance that has the same kind of molecules throughout. One molecule of salt, sodium chloride, is a sodium atom bonded to a chlorine atom, and when we have, you know, a shaker full of salt, that's a compound of sodium chloride. Everything in it is a molecule of sodium chloride because they bond together. Carbon dioxide, the bubbles in your soda, are bonded together. Those two atoms fuse together. They're sharing electrons. That's why they're bonded together. Okay? In nonmetals, they often will combine with other nonmetals to form what we call diatomic molecules. Di means two. So these are atoms made of two of them. Like, for instance, oxygen. When we have oxygen like in the air right now, it naturally will not exist as just a single oxygen atom here and a single oxygen atom here. It likes to work in pairs. It'll pair up automatically and make these little molecules, O2, N2, H2. That's how those gases typically occur, bonded to one another in pairs. And again, you're going to see why they like to bond like that, but it has to do with the electrons again. They're so important. Families of nonmetals, okay? Well, we already know that the groups or families are the vertical columns. I just pulled out some of those vertical columns, the ones that are nonmetals. And we know that hydrogen, even though it's over there on the far left, is not a metal. It sets apart. Okay, don't get thrown off by the fact that it's green in this particular example. So we call that the hydrogen family. And then we've got the oxygen family. Well, everything below oxygen is in the oxygen family. The halogens are the next to last group, group number 17. The noble gases are group number 18. Okay? Now, what did I say was the magic number for electrons in the outer shell? 8. These gases, the noble gases, guess how many electrons they have? 8. They are happy little campers. They're like a king, a noble person. They have everything they need. They don't need to consort with the little people. They have all their 8 electrons. As opposed to this group right here, guess how many they have? 2. Well, if this has 8, this one must have 7. So they're short one, almost close to having that perfect arrangement. All they need is one more. What kind of atoms do you think they're looking to combine with? They got 7, they want 8. They're looking for atoms with 1. Okay? Are you starting to see the secret behind all this? The 7s want the 1s. The 6s want the 2s. So if we know about the number of electrons that are in the outside, it'll give us a clue about what they're going to do. They want to combine, because when the 6s combine with the 2s, atoms with 6 electrons on the outside combine with those with 2 on the outside, they now collectively shared have 8, and they're happy, they're stable. Metalloids. 1, 2, 3, 4, 5, 6, 7. Some will argue that there's another one that belongs in metalloids, but these are the ones we're sticking with. 7 elements on the border between metals and nonmetals. The most common metalloid that we use a lot in electronics would be what? Silicon. Or silicon, not silicone. Silicone's something different. Silicon. Silicon, as in Silicon Valley, is what they make all those little chips out of. All the ICs, all the computer chips. the main electronics in your cell phone, in your calculator, in your DVD player, MP3 player, you name it, is made of silicon. It is a special metalloid that acts kind of like a metal, like a conductor, when it's next to certain other elements, in the presence of other elements. So we can use it as a semiconductor. We use silicon in the little IC that was in your circuit. Germanium was the element that made up that diode, that clear glassy looking diode that was in your crystal radio. So those are real important to us, semiconductors. All right, now the periodic table. This is the key point from today's lesson that I want you to be able to take away. Because when you understand about these valence electrons, you can predict what will combine with what. We're looking at a section of the periodic table. And you can see some of the groups represented here. We skipped several in there. We skipped 3 through 12. But if you look at groups 1, 2, 13, 14, all the way up to 18, do you see a pattern here? If you're in group 1, how many electrons are orbiting around the nucleus? 1. What you're seeing here, by the way, is called a dot diagram, electron dot diagram. And you might do those later on in high school. Okay, if you're in group 17, how many electrons do you have in your valence shell? 7. If you're in group 15, if you're in group 14, do you see the pattern? Okay, if you look at this first digit, the ones digit, if you're in group 18, we call those the what gases? Noble gases. They all have how many valence electrons? 8. That digit, that first digit, right there, tells me that they're going to have 8 electrons. If you're in group 13, that digit tells me you're going to have 3 electrons in the outer shell. Remember, that's the important one that will decide what you're going to react with and how you're going to react. If you're in group 1, you're going to have 1 electron in the outer shell. Get it? Okay? This is a key thing, and you need to know that, how we figure out the number of valence electrons so that you can complete the back side of this. Valence electrons determine how chemicals will react or bond. Okay? So what's here in the outermost shell is what's most important. Now, if you look at the periodic table here again, we do have some exceptions. Science does this a lot. They make rules, you know, kind of like they do in language arts. I before E, except after C. Well, we can use our group numbers. We know this is group 1, this is group 2, this is group 13, 14, 15, 16, 17, and 18. All we have to do is look at that first digit, and that tells me that all of these have how many valence electrons? And all of these have 2. The question is, what about a lot of these transition metals? And you already read that most transition metals have how many electrons? Should have written it in your notes.
3.
1, 2, or 3. Some of these break that group rule. Like this would be group number 3, and you'd expect all of these to have 3 valence electrons. But what you have to do is look up here first for the exceptions. You see how it says groups 3 through 12 have 2 electrons? All of these are going to have 2 with some exceptions. These are the exceptions. These all have 1 each. Okay? And there's a couple other exceptions. PD, which you probably won't get too much, has no valence electrons. And helium, which is over here, we would expect it to have how many? 8. In fact, has 2. Okay? So what you need to do when you're filling in the back side of this metals and nonmetals is you need to look at the group number. If it's in 1, 2, 13 through 18, then you can go with that first digit. If it's in this area, though, look at the exceptions first. If it's not one of these, then it's going to have 2. Yes?
How could something have no valence electrons? Because if it has electrons, maybe that outer wall would be valence electrons.
That's a good question. I don't know the answer to that. Okay? The last column there, metals, nonmetals, or metalloids, that's what you just did in shading in the table. And I'll put a copy of that up here so you can refer to that. Okay, so I'd like you to work on filling in this table. Notice there's also 3 questions below it there that should be answered in complete sentences. We know that the periodic table is organized according to the number of protons, which is also the number of electrons. So you simply look at the atomic number, and you know those two. And you can find the number of neutrons by doing what math? Subtract the protons from the rounded mass. That's the key. You've got to round off that mass first. So as you start work on this one, protons, neutrons, and electrons, you should be able to do everything in here with the exception of the last column. We already know that the group number there that you're going to fill in this next to last column is also the number of, or the first digit is the number of valence electrons. Okay? What we're going to write in this final column is a series of numbers that will reflect which electrons are where. How many are going to be in the first shell? That first, here's my nucleus, my first little orbit. How many are going to be in the second orbit and the third one, and so on. Okay? And there's a simple step-by-step procedure that you can follow that I've listed here at the top. I'm going to guide you through one example. Okay? First of all, you take the element. You got to know what element it is, so hopefully you can figure that out from the numbers that are left there. And you have to know several things about it. You have to know the period that it's in, the group that it's in, and its atomic number. If you know those 3 things, everything else will fall into place. Silver is atomic number what? 47. Okay? If it is atomic number 47, how many protons does it have?
47.
How many electrons? 47 electrons, okay? And to find the number of neutrons, we just subtract the 47 from the atomic mass of, what is it for silver? Okay? You got to round it off and subtract it. So that's easy to do. We know how to do that. We know how many electrons there are, but we don't know which are in which shells, how many are in which shells. That's an important thing to find out. So first we're going to figure out how many shells it has. And according to this, the period number is the number of shells. What period? Which row is silver in? Row, not column. 5. It says it right here, guys. Okay? It's in row 5. You still with me? You look at the columns and it's in row 5, which means it has 5 shells. Okay? Now if we look at this thing, don't get thrown off and all confused by this. What we've got here is our protons and neutrons that make the nucleus of our atom. And going around the outside are electrons. Some are going to be close in the first orbit. Some are going to be farther away in the second orbit. Some are going to be farther away in the third orbit. You're still with me? Okay, so each of these represent a shell, an orbit. Okay, these are closer than these. And the way it works is we fill in those shells that are closer first. In most cases, what you have to see here is that within each of these shells we have suborbitals. We have different orbit shapes. The S, the P, the D, the F. They actually describe the shape of that orbit. You know, not all the orbits are very simple round or elliptical orbits. There are all sorts of bizarre things that the electrons do in their orbiting pattern, okay? And these describe the shape of that electron cloud, if you will, okay? All different shapes that they can occur in. And you're going to get into that more later on in chemistry. I'm just pointing out that that's what the letters mean. And the 1, 2, 3, 4, 5, 6, 7, those refer to the shell or energy level. Okay? If my atom takes up 5 shells, like silver, 1, 2, 3, 4, 5, where will the valence electrons be? In shell number 5. It takes up 3 shells for its electrons. Where will the valence electrons be? In shell number 3. Okay? So that's what the numbers mean. Now you know what the letters mean. The little numbers up above indicate which electrons are going to be in this shaped orbit, which electrons will be in this shaped orbit. And they follow certain rules. Okay? So we already know that this is going to have 5 shells. 1, 2, 3, 4, 5. This will be the last shell with the valence electrons in it. By looking at the group number, we can now figure out how many valence electrons. What group is gold or silver? 11. And it also says it right here. Okay? If it's in group 11, how many valence electrons? 1. Where would I write that 1? If their valence electrons are going to be in which shell? The 5th one, right? The outermost shell. 1, 2, 3, 4, 5. So I know that in this last shell, we have 1 electron. Still with me? Okay? What I did is I used the period number to figure out that I was going to have 5 shells. I know what the last one's going to be because the group number tells me that. 1 electron. Okay? Remember, there are some exceptions in groups 3 through 12. You got to look on your sheet for that. Then all I have to do is fill in this. Well, if I have 1 electron here, 47 total, how many are going to be in this? 46. So this should be 46 electrons. The next part is just adding up. We got to make 46, and we've got to do it by following these arrows. Still with me? Okay. I got a 2 right there. I got to fill that one up first. Gives me a grand total of 2 for the first shell. Okay? I got another 2. 2 plus 2 is 4. Okay? According to the arrows, I then go over here. Plus 6 is 10. Okay? So I've got 8 more here for a total of 10. And then I've got to fill up this shell, which is 12. That's my running total. Plus 6 is 18. Plus 10 is 28. Okay, so I got 28 total at this point. In this shell I have how many? 18. 28 total, and I need what? 46. Okay, so actually, oh, I skipped. I'm sorry. I'm supposed to come down here, right? Got to do 2. Add 2. 28 is 30 plus 6. What is it? 36 plus 10, 46. 10, 6, and 2 is 18. Okay? I did that wrong because I didn't follow my own arrows. I should have filled this one in first before I did that one. Do you see that? I should have circled that number first and kept my running total. Once I hit that 46, I stopped filling these in. Now, it worked out nice because it came out to a perfect 10. Not always. That may have just been 8 that I put in there. Okay? But I fill it up. I can only fit 6 here. So, you know, if I have 7 more electrons, it's got to be 6 here and 1 here. You see what I mean? That's the maximum number I can put in there. So this now is referred to as my electron arrangement or electron configuration. And you would just write it out as 2, 8, 18, 18, and 1. There's my 1, 2, 3, 4, 5 shells, and I have 1 electron in my valence shell. Let's do a few more examples so you got this down. Okay? This might look a little familiar. Don't forget about the exceptions for valence electrons up here. P is phosphorus. I won't write the whole thing there. Atomic number 15. What's its rounded off mass? It asks you to round it off. What? 31. Number of protons? 15. It's going to be the same as the atomic number. Number of electrons? 15. So if I have 15 protons, how many neutrons do I have to have? 16. 31 minus 15 equals 16. Okay? All right, so I got all those filled in. Group number. What group does phosphorus belong to? Okay, so it's over here. Group, you said 15, 16, 17, 18. That's right. Group 15. So if it's in group 15, how many valence electrons does it have? 5. This digit here tells me it's going to have 5 valence electrons. Okay, so I already know this last number here is going to be a 5. Now, how many shells? What period is phosphorus in? Period what? 3. If it's in period 3, that means there's going to be 3 shells, 3 numbers there. Now let's go back and use the thing again. Get rid of all this. Okay. So we have 3 shells. How many are in the last shell? 5. And I have a total of how many electrons?
47.
How many electrons? In that one. I have 15 total. So if I already took 5 away for the last one, this is going to leave me with how many in here? 10. 10 are going to be in there. I have to fill this one up first, then I follow the arrow and I go to this one next, and then I follow the arrow and I do this one next. 2 in this energy level, 8 in this one, for a total of 10. Okay? 2, 8, and 5 would be what I would write there. Okay? Now that worked out really easy. Came out to nice even. They all filled up totally. It's not always going to work that way, but you always will follow the arrows. Let's do another example. Okay, so we don't know anything here but the number of protons. But if we know the number of protons, we know the atomic number is 20, which means it's element calcium. Ca, calcium. Okay, if it's got 20 protons, it has 20 electrons. The atomic mass of calcium rounded off is 40. 40 minus 20 is 20. It's keeping it really easy here. It is in group number 2. Okay, we check and make sure. Is calcium one of the exceptions? No, it's only stuff in 3 through 12, so we're okay. So, well, with the exception of helium, okay? So, there's 2 valence electrons, we know that. How many shells? What period is it in? 4. So there's going to be 4 shells here for a total of 20. So we're going to have a number, a number, a number, and then 2. So we've got to figure out what that is. Go back here again. Grand total of 20 electrons. How many shells again? 1, 2, 3, 4. In the 4th shell we have how many? 2. Okay, so the balance, the rest that have to be in here are going to be 18. 2 plus 2 is, plus 6 is, plus 2 is 12, plus 6 is, let's see, it worked out so nice that time too. In this row, total of 2. In this row, total of 8. In this row, total of 8. 8 and 8 is 16, 17, 18, 19, 20. There we go. So the number you would write would be 2, 8, 8, and 2. You guys getting a handle on this? Yes. Do we need to do another example?
How come you did that over 10?
Huh?
How come you did that over 10?
Because I don't fill this one until this one's been filled. See? We filled that one. We're following the arrows. Good question. Why didn't I do the 10? Because I follow the arrows. Okay? This orbital gets filled before this one does, or suborbital. All right.